It is a foundational rule of electromagnetism. Whenever electrical charges move, they are instantly surrounded by a magnetic field. But a standard bar magnet presents a paradox. It is a solid, cold piece of iron with no batteries and no apparent moving electricity, yet it possesses a powerful magnetic field. We can see the shape of that field by looking at iron filings. They align into distinct, closed loops that flow out of one end and return through the other. When we place this magnet side by side with a current-carrying solenoid, the results are startling. The macroscopic shape of their magnetic fields is virtually identical. André-Marie Ampère looked at the similarity and proposed a radical hypothesis. These two objects look the same because, at a microscopic level, they are the same. To explain the equivalent solenoid, we zoom into the iron's surface, visualizing a uniform grid of spinning electrons, each acting as a miniature current loop. In this view, the pulling power of a solid magnet would be the cumulative result of these billions of microscopic internal circuits. To turn this hypothesis into a proven law, we have to see if the mathematical formula for a solenoid's field matches the known formula for a bar magnet. We begin modeling a finite solenoid with radius a and length 2L. We identify our observation target, point P, located far out on the central axis at distance r. For this test to work, r must be significantly greater than the solenoid itself. By treating this cylinder as a stack of thin circular loops, we can use calculus to sum up the magnetic influence of every single loop at point P. This geometric model is the only way to convert visual observations into empirical proof. After performing the integration, we arrive at the resulting equation for the solenoid's far axial field. B equals mu naught over 4 pi times 2m over r cubed. This matches the established formula for a bar magnet's field. The two expressions are identical. This proof hinges on the variable m, the magnetic moment. We've shown the magnetic moment of a bar magnet equals that of an equivalent solenoid. The math removes the distinction between a coil of wire and a solid chunk of iron. Both generate force through the exact same mechanism. With the solenoid model mathematically established, we can use it to explain a behavior that has consistently defied standard intuition. If you break a bar magnet in half, you never end up with an isolated north pole in one hand and a south pole in the other. You simply get two smaller, complete magnets. This is easier to visualize if we look at our equivalent solenoid. Picture a wireframe coil where the field lines flow continuously through the center and return around the outside. Think about what happens when you slice a continuous coil of wire in half. You haven't separated the poles. You've created two shorter solenoids. The field lines immediately reroute, maintaining a continuous entry and exit point for each new half. This explains why isolated magnetic poles, or magnetic monopoles, cannot exist. Unlike electric charges, magnetism requires a continuous path. The equivalency principle suggests a magnetic universe defined not by individual charges, but by unbreakable, infinite loops of current.